To evaluate education, you must first quantify it. Before a teacher can assign a grade, or a student can gauge their own progress, the chaotic process of human cognition has to be mapped onto a mathematical structure. This active measurement is the baseline consensus of the classroom. It provides the objective data that both educators and learners rely on to judge the reality of their work. The science of extracting that data is called psychometrics. It is the discipline dedicated to capturing invisible, complex traits, like intelligence and learning capacity, and translating them into hard numbers. Pinning down a latent mental trait requires extreme precision. You need highly valid instruments, meticulous data collection, and rigid analytical frameworks to ensure the numbers actually reflect reality. Achieving that precision took decades. The methodology evolved from early theoretical models of intelligence to tests based on biological milestones and eventually arrived at the universal standard deviations we use today. Rigorous measurement serves as the epistemological foundation required to make any assessment of human learning objective and meaningful. The attempt to strictly measure the human mind began in the early 20th century. This marked the formal birth of psychometrics. In 1904, a psychologist named Charles Spearman introduced a mathematical technique called factor analysis to evaluate cognitive performance. This network diagram visualizes Spearman's resulting theory. The large central node represents what he called the G factor, or general factor. He proposed this as a common mental capacity shared across all cognitive tasks, while the satellite S nodes represent specific aptitudes, like musical or mathematical ability. By tracking test results, Spearman observed a clear statistical correlation. Strong performance in one specific skill area reliably predicted strong performance in others. The central G factor linked them all. By isolating G, Spearman provided the first theoretical, quantifiable baseline for general intelligence. He proved that abstract intelligence could be treated as a single mathematical variable. That breakthrough cleared the way for researchers to build empirical, standardized tests for the classroom. In 1905, Alfred Binet and Theodore Simon applied this approach to education, creating the first metric scale to identify students with severe learning difficulties. This document is the Binet-Simon scale. Looking strictly at the left column, you can see that they organized specific cognitive capabilities into strict, age-based milestones. The expectations for a 6-year-old in 1911 were highly specific. A student needed to correctly count 13 coins, define simple daily words, and copy a drawn rhombus. Comparing these early benchmarks against the 10 and 12-year columns established a specific scoring metric, mental age. If a chronologically 10-year-old child successfully completed the puzzle tasks designed for 12-year-olds, their recorded mental age was officially set at 12. In 1912, the German psychologist William Stern formalized this age-based relationship into a permanent mathematical formula. This formula calculates Stern's intelligence quotient, or IQ. You take the student's mental age, divided by their chronological age, and calculate the ratio in months. Because the formula relies on a subject's chronological age as the denominator, Stern's quotient specifically measures the rapidity of cognitive development over time. Mental age provided a logical baseline for evaluating children. However, because it relied entirely on biological pacing, the math was about to break down. Stern's formula contains a fatal mathematical flaw. Human cognitive development plateaus in early adulthood. Dividing a 60-year-old's test score by their chronological age yields a mathematically absurd result. The psychologist David Wechsler recognized this limitation. To evaluate intelligence universally, he stripped the biological timeline out of the equation entirely and replaced it with a statistical distribution. This animation shows Wechsler's model. The concept of age shatters, and raw performance data reforms into a normal distribution bell curve. The mean is forced to exactly 100, and the standard deviation is set at 15 points. This setup dictates a specific reality about test scores. Earning a score of 110 does not mean a person is 10% smarter than the average subject. A standard IQ only indicates statistical rank. A score of 110 simply means that the subject performed better than 25% of peers taking the exact same standardized tasks. Psychometrics stopped measuring absolute levels of biological development. Instead, it began calculating relative statistical rank within a population. To make that relative ranking work across thousands of different classrooms and exams, statisticians rely on an underlying mathematical engine known as the z-score. This equation defines the z-score. It calculates exactly how many fractions of a standard deviation a raw test score is positioned away from the class average. The z-scale imposes strict uniformity. No matter what test is given, the converted mean is permanently set to 0, and the standard deviation is always exactly 1. Bounding the data reveals a predictable spread. 99.7% of scores fall safely between negative and positive 3. Watch a live conversion. An arbitrary score feeds into the equation and lands exactly at the +2 standard deviation line. This yields extreme precision. If a student achieves a z-score of positive 1.96, the math dictates that only 2.5% of the tested population score higher. For educators, this solves a massive logistical problem. They can take vastly different, highly localized classroom tests and compare them objectively on a single, mathematically pure scale. Standardizing scores via the z-score provides the rigorous statistical mechanism required to evaluate human learning on a mass scale without local bias. By the 1960s and 1970s, this rigorous statistical framework was fully integrated into everyday educational policy and mass classroom evaluation. Educational measurement branched into two distinct practical approaches, formative and summative. This looping cycle represents formative evaluation, deployed actively during the learning process to help students adjust. When the loop hits a hard checkpoint, it becomes summative evaluation, the definitive measurement used to judge outcomes and issue credentials. Whether the goal is formative coaching or a final summative judgment, educators rely on the statistically valid instruments developed and refined over the 20th century. The methodology matured from Binet asking children to count coins in Paris to Wechsler universally mapping intelligence through z-scores. We no longer evaluate how biologically old a mind is. Instead, we use rigorous mathematics to map precisely where a learner stands relative to a population, securing the data required to make educational progress visible.